Alright, so this is our Honors Chemistry Section 8.4 lesson video, Part 4. And really this is kind of an extension of Section 8.4. And so now we're going to go into orbital hybridization. In this video part, Part 4, I'm just going to kind of explain how it happens and what it looks like. And then in Part 5, we'll actually do some questions based on hybridization. So, in the Lewis theory, covalent bonding occurs when atoms share electrons. In the valence bond theory, we visualize the buildup of electron density between two nuclei as occurring when the orbitals of the atoms overlap. The overlap of the orbitals allows two electrons of opposite spin to share the common space between the nuclei, forming a covalent bond. So it would look something like this. If two s orbitals overlap, this would be the overlapped area where the two electrons would be. And if an S and P overlapped, because we all know P has the two lobes, if S and P overlapped, it would look something like this. Or if two P orbitals overlapped, it would look something like this. So that's kind of what's going on when atoms share electrons, is their orbitals overlap and the electrons are in that overlapped portion. So the bond length of a covalent bond corresponds to the medium of the potential energy of the curve. So if the two nuclei are too close, they start repelling one another, so energy is high. And then as it gets further apart, the attraction's not there anymore. So there's always this sweet spot, and so this is what the energy curve looks like. And so this lowest point is where you would have your actual bond length, because it's kind of like Goldilocks. Like, here we're too close, they start repelling. Here we're far apart, they can't attract well enough, and here it's just right. So why do we have hybrid orbitals? Well, to explain the geometries of the molecules that we learned when we did Vesper theory, we assume that the atomic orbitals on an atom mix to form new orbitals called hybrid orbitals. The process of mixing atomic orbitals is called hybridization. The number of hybrid orbitals must equal the number of atomic orbitals. So like if you're going to hybridize 3 orbitals, you have to get 3 hybrid orbitals. It's not like you can start with 3 and you hybridize and end up with 2. So you always have to end up with the same amount you start with. So like here, I have an s orbital, I have 2 p orbitals, and so if you look, I end up with 3 hybrid orbitals like that. All right, so let's look at how this happens. And it's based on electron configuration. So first we're going to start with sp hybrid orbitals. So BeF2, we know, looks like this right here, because remember, Be is one of our exceptions to the octet rule. It tends to surround itself with only 4 valence electrons. These two bonds are identical on Be. So if we look at the electron configuration for F, it needs 1 more electron. So this shows that F can bond by filling its 2p sublevel. So that makes total sense. F wants to share an electron in that 2p sublevel. However, Be looks like this right here. It has a full 1s and a full 2s. So really looking at that electron configuration, it's kind of like, Be's already kind of full, like doesn't want to bond at all. Because I mean, it's going to take a lot to fill in an entire 2p sublevel. So since Be has no unpaired electrons, it should not want to form bonds. So one of the electrons is kind of promoted to a 2p orbital. Okay, so they were 1 up, 1 down, and 2s. And so 1 kind of goes to 2p. That way they have a chance to pair up and finish those orbitals. However, if this was what was happening, then the BeF bonds wouldn't be equal, because 1 would be with an S and 1 would be with a P. So the 2 bonds should kind of be different. Like it kind of looked like this right here. We know we're using P for F, and so one of the bonds would be Be's s orbital overlapping a P. So that would look like this. And then one of them would be Be's p orbital overlapping with the P on F. So see, those 2 bonds then would not be the same, they would be different. But we know through experimentation they're the same. So that's where the hybridization comes in. So look carefully at where we're starting. So we have 1 and 2s, and we have 1 electron and 2p. So So what happens is we take our s orbital and our p orbital and we form sp hybrid orbitals. Now because I'm starting with two, an s and a p, I end up with two hybrids. And so because s is just a sphere and p is two lobes, the sp orbital kind of looks like just one big lobe and then a little one. So it's kind of like s and p have come together. And so then when we draw them together, it would look like this. So I know this is kind of tricky and looks like it's just a normal p orbital, but remember you technically have the other little baby side kind of right here and right here. They're just overlapping one another. And so if we rewrite the electron configuration, we rewrite it like this. We say that these are just sp orbitals. But notice our other two p orbitals are totally normal. We did not hybridize those, okay, because they weren't needed. So the remaining two p orbitals are the same on BE. The hybrid orbitals and bonding in BeF2 would look like the following diagram. So F just has its normal p orbital, and it's overlapping with the new hybridized SP. And so remember, there's technically that other little lobe that's on the other side. Because it's so small, we tend to just not put that in the drawing because it kind of overlaps with everything. And so then that's what it would look like, and that makes both bonds identical. Whenever we mix a certain number of atomic orbitals, remember we get the same number of hybrids. So if I mix 3 atomic orbitals, I'm going to get 3 hybrids. Each of the hybrid orbitals is equivalent to the others, but points in a different direction. So if you noticed in our last ones, it was 180 degrees apart. Thus, mixing one 2s and one 2p orbital yields 2 sp orbitals that point in opposite directions. So when you have 2 opposite directions, of course, is at 180 degrees. If you have 3, they'd all be at 120 degrees from each other. 4 would make a tetrahedral shape. They'd be at 109.5 degrees from each other. All right, so let's look at what is sp2 hybridization. So an example is BF3. So we know BF3 looks like this. Of course, our Fs do need 6 lone electrons around them to be technically correct, but it looks like this. So again, F needs 1 electron in its 2p orbital, so it makes total sense that it would want to form 1 bond, and so then it would fill that 2p sublevel. However, B looks like this. Boron has this electron configuration. So it appears that it really kind of only needs to bond once to finish up that 2p, and that these shouldn't want to bond at all because they're already paired up into S. So what we're going to do is something similar before. So since boron only has 1 unpaired electron, it should only form 1 bond. So one of the 2s electrons is promoted to a 2p to allow for 3 areas to bond. Because when they bond, what they're trying to do is pair the electrons. So if the electrons are already paired, it shouldn't want to bond. But we know it forms 3 bonds. And remember, boron is one of our exceptions to the octet rule, where it tends to surround itself with 6 electrons. All right. However, this arrangement would not make all the bonds equal, because this bond would have an S sublevel, but these two would use a P sublevel. So there should be a different oddball bond, but there's not. All the bonds are equal. So that means we need to do some hybrid orbitals. So we take the S and the 2 P's, and see, we make those sp2 orbitals. And the reason it's called that is it was 1 S and 2 P's. So our first example was sp because it was 1 S, 1 P. This example is sp2 because it came from 1 S and 2 P. And so we took our 1 S, our 2 P's, and then we get 3 hybrid sp2. Okay, remember, 3 atomic orbitals equals 3 hybrids. That remaining 2p orbital, though, remains the same. So it is not a hybrid. So only the orbitals that need to become hybrids will be. So the hybrid orbitals and bonding in BF3 would look like the following diagram. So we have our normal 2p orbitals from our from our fluorines, our Fs. And then we have those new hybrid sp2 orbitals. And I like this picture because it still shows that normal 2p orbital left over. okay? Because remember, that one is not hybridized. So let's move on and look at our last one, which is sp3. So hopefully you're noticing a pattern here. So we'll look at CH4. So H has one unpaired electron, so of course it wants to use this s orbital to overlap and finish off its pairing. So it shows that it's going to bond by finishing that level. But if you look at carbon, clearly it has 4 bonds here. It seems like it would only want to form 2 because there's the only unpaired ones. So, of course, hopefully you realize what we're going to do is promote our electrons so they're all unpaired. Because remember, we know electrons can move to different energy levels and things like that. So since C has 2 unpaired electrons, it should only form 2 bonds. So one of the electrons is promoted to 2p. But again, this arrangement would not make them equal because one bond would be a 2s orbital overlapping and the other 3 would be with a 2p. So that's why we hybridize. So we're going to take all 4 of them and hybridize them. So because it's 1s and 3 p's this time, we call it sp3. So there's 4 hybrid orbitals, sp3. All right, so we take our s, our 3 p's, and so if you look, we get a tetrahedral arrangement because remember, they all point in opposite directions. So it's following our Vesper theory. So the hybrid orbitals and bonding in CH4 would look like the following diagrams right here. Okay, and so again, here you can see that extra little lobe, but when they put them all together, they normally don't put the lobes anymore. All right, so that is how hybridization works. Now, I know you might be thinking, wait a minute, we didn't do any example problems. That'll come in part 5. I just didn't want this video to be excessively long like all the rest of them are. Okay, so this was just me explaining how it happens, and so now we'll kind of go into, in part 5, how to do questions about it.